To Demystifying WebRTC, my talk on the protocols which power audio and video calls worldwide. The first question you might ask upon hearing about this talk, why do I care, right? Conferencing, video conferencing, audio conferencing, this is the original use case WebRTC was intended for, but it has expanded from there to fit in a lot of other use cases, which are shown here. Broadcasting, live broadcasting is, it typically uses RTMP, but WebRTC is growing increasingly popular here owing due to the fact that it is an open standard, it is free and open source. There are implementations available in pretty much every single language out there, and it is freely available in the browser. WebRTC is in every single modern browser out there. Remote access, ever use TeamViewer? WebRTC can do that. File sharing and censorship circumvention. Now this is a fun one. WebRTC is not only for audio and video, it can be used to share pretty much any data anywhere. Why is it suitable for file sharing and censorship circumvention? Because number one, the clients are freely available. It's there in the browser. If you have a browser, you can use WebRTC. Second, if people try to block WebRTC in their firewalls, for example, it's going to disrupt a lot of other services, such as video conferencing. So it's less likely that they're going to be censored. Internet of Things, you can connect your video cameras using WebRTC. You can use WebRTC to talk to remote sensors. Media protocol bridging, have you ever dialed into a meeting? I mean, maybe not the students here, but the working professionals here. If you dial into a meeting, WebRTC is what bridges your browser to SIP, which is the, the phone call which is happening. So that's why you should care. And so what is WebRTC really? It's a protocol. It specifies how two agents can negotiate bidirectional, secure, and real-time communication. Real-time is important. It's also an API. The API allows developers to use the WebRTC protocol. It's an open standard. There are RFCs going around. Everyone can contribute. There are multiple free and open source implementations. It's widely available. Every single major browser today supports WebRTC. It's the industry standard. If you've used Google Meet, Zoom, all of them use WebRTC. And it's mandatorily encrypted. So communication between two peers, it is encrypted by default. There are 4 steps to success in a WebRTC call. Let's break them down one by one. Signaling is the first step. When we start out with 2 peers who want to communicate, for example, I want to talk to my friend who is in another country, let's say. They have no idea who to communicate with and how to reach the other person. We don't know their IP address. We don't know pretty much anything about them. Signaling is the step that solves this. It bootstraps the call by exchanging some data between the 2 peers. It uses an existing plain text protocol. You might be used to sending data over JSON. WebRTC prefers to do this over SDP, session description protocol. Each SDP message is made up of key value pairs. They contain information such as the IPs and ports that the other agent is available on. These are called candidates. The number of audio and video tracks that the agent wants to send. The audio and video codecs each agent supports. And some other values used for connecting, the user fragment, user password. We really don't need to dive into this. And the certificate fingerprint. I mentioned it's encrypted by default, certificates. Right. WebRTC uses the offer-answer model. One agent offers, the other agent answers if it is willing to accept what has been offered. And this gives the answer a chance to reject unsupported codecs. For example, Safari, the browser, it does not support VP9 codec. So let's go over the SDP spec. As I mentioned before, it's a key value pair. We don't need to look at the VOST and C. These are essentially constants when used in the WebRTC context. But we should look at M and A. So M stands for a media description. This is essentially a list of values about the media streams and what codec they're using. And A, this is a free text field. You can set literally any textual value to this, and this is the most commonly used line in WebRTC. Let's take a look at an SDP's example. This is an SDP. This is how it looks. It's a blob of text. Let's just break this down a little. The fingerprint. This is a hash of the certificate that a peer is using for DTLS. DTLS is essentially TLS, but for UDP. After the DTLS handshake is completed, you compare this to the actual certificate to confirm you're actually communicating with who you want. This line group bundle, it's just saying that you send all your media over a single connection. And these are the candidates. These are the most important. This is one possible address that the WebRTC peer is available on. And finally, we have the media description at the bottom, which I'm breaking down in the next slide. This is a media description. Let's go over it. The most important part, MID. It's used for identifying media streams within a session description. And next, we have the RTP map. If you look at these two lines, the one at the top and the other one which is highlighted down here, they both have this section that says 111, 111. What this is essentially saying is this particular media description is for audio, and it's using the codec defined at 111. And this line says the codec defined at 111 is Opus, the Opus audio codec. Next, we have the FMTP line. It's just a few extra parameters for the codec that is being used over here. And finally, these are the SSRCs. These are synchronization sources. For example, a video from your webcam, that's an SSRC. Now that, now that we have signaled, let's get to connection. Very often, the other WebRTC peer will not be on the same network. How often is it that you're on the same network when talking to someone over a Google Meet or Zoom, whatever? Very uncommon, right? Calls typically go over the public internet. Some networks, they don't allow UDP traffic at all. Some don't allow TCP. There's a lot of parameters that network administrators can change, which will make our life difficult as WebRTC engineers. Almost every single user on the internet is behind a NAT device, network address translation. Now, this is helpful for ISPs to avoid IPv4 exhaustion, but this causes massive headaches to us as WebRTC folks. Now, if you don't know what NAT is, it's a method used by routers to allow multiple devices to run on a single public IP. How it works is it modifies the request as they're going through it. It changes the internal private IP address to the router's public IP address. And it maintains something called a NAT mapping table inside it, where it maps each internal IP to a port exposed on the router. So let's say you have a phone which is connected to your router, and you send a request to google.com. Now, your NAT device is going to create a NAT mapping. Let's say your phone is at 192.0.0.1. So it's going to make a mapping of that to a public port on the NAT device, let's say 56,000, right? Something like that. So what Google is going to see the public IP and the port 56,000, something like that. And so when it sends its data back, it will send it back to that port. And using that table, the NAT is going to understand that at port 56,000, it was your phone. So it's going to send that data back to your phone. And this is important in the context of WebRTC because the other peer, it only has your public IP address. It does not have your private IP address. So we need to know that NAT mapping. How do we do this? We do this using something called STUN. STUN is an existing standard, and this is another great example of how FOSS, free and open source, has benefited WebRTC. It didn't think it could do everything better just by itself. No, it built work on others' work. It used existing technology and combined them together to make it the best that it could be. So STUN stands for Session Traversal Utilities for NAT. It allows for the programmatic creation of NAT mappings, and it also gives you the mapping details. So suppose, as I mentioned in my example earlier, when you make a request to Google, it creates a NAT mapping, but you don't really know the result of that mapping. With STUN, you can send a STUN binding request to the STUN server, and the server is going to respond with a STUN binding response, which contains the sender's public IP and the port which was bound by the NAT mapping. And this information is included in the SDP that you exchange with the other peer during the signaling process. I mentioned those candidates earlier. They get their data from STUN over here. However, all is not fine and dandy in WebRTC town because this information may not be enough to connect to the other peer. Why? Some NATs are nasty. They don't like other peers connecting in if they have not connected first. So if you haven't talked to Google earlier, it's not going to allow Google to send you a request just like that. In the same way, if you have not talked to the other peer earlier, it's not going to let the other peer send audio video to you. What do we do in this case? Just a nice diagram first turn. What do we do in this case? We use turn. Turn, another standard. Traversal using relays around NAT. What this is effectively, it's like a forwarding address. Instead of just getting your own NAT binding, you're going to send an allocation request to a turn server, and the turn server will give you an IP address and a port, and you'll send this IP address and port to the other peer. And essentially, the other peer will send data to the turn server, and the turn server will forward it to you. So you may ask, why don't we do this all the time? Why do we have to do all this NAT finagling, right? You can just use a turn server all the time. No, there are some disadvantages. There is increased latency, packet loss, and jitter. Turn servers are expensive to host. They use up a lot of resources and bandwidth. It is for this reason stun servers are essentially free. Google hosts free stun servers, but turn servers are paid. At work, we use Twilio's turn servers. We can also host our own, but yeah, they're paid. Now, finally, we have the information needed to connect, right? We know the other's public IP address and NAT mapping port. How do we actually connect using this? We use a standard called ICE, Interactive Connectivity Establishment. And this is how WebRTC connects to agents. It determines all possible routes between two peers and selects the best one. And after connectivity is established, you can send literally any data over it. It behaves like a regular WebSocket if you have used those. And a route, it's like a pair of local and remote IP addresses. So it tries all possible routes between them and selects the best one. How it works is they just start sending traffic on each pair, and all the ones that actually saw traffic go through, they're promoted to a valid candidate pair. And in ICE terminology, there's a controlling agent and a control agent. These are chosen by random. And the controlling agent, it will nominate one of these pairs and attempt one more round of communication over that pair. And if successful, is going to use this for the rest of the session. ICE is a complex protocol, and to understand more, please head over to this link. I have shortened it for your benefit. It's a blog I wrote on the internals of ICE. Finally, we have a connection. We have a bidirectional socket-style connection over which we can send anything we want. How do we actually send media over it? Why is media important? It's pretty much the most common use case for WebRTC. So media communication with WebRTC. It's going to use two pre-existing protocols. Again, this is a common theme with WebRTC. It's going to use pre-existing stuff. RTP and RTCP. It uses these protocols. RTP stands for Real-Time Transport Protocol, and it carries the actual media. And RTCP is a meta protocol. It carries metadata about the call. It's very flexible. It allows you to add any metadata that you want, but by default, it's going to give you some tools to handle changing network conditions and handle congestion control. For example, it's going to give you the number of packets sent, the jitter in the connection, things like that. Now, a little bit about video 101. Let's not get to audio, but video here. Essentially, we need to compress the video that we are sending because a video file by itself is huge. There are two kinds of compression, lossy and lossless. Video can be encoded to be lossless, and there is no data loss. But lossy, it's just going to ignore some bits of that. In general, WebRTC prefers, not WebRTC, RTP prefers lossy compression because exact quality is not a requirement, but real time is a requirement. And there are two standards commonly used for lossy compression. There's intra and inter-frame compression. So what intra-frame compression does is it reduces the size required by each frame, but it's not dependent on any of the other frames. This is commonly used in other compression for single images, such as PNG, JPEG, whatever. On the other hand, inter-frame compression, it looks for ways as to not send the same information twice. For example, if you have a if you have a video stream where there's not much changing, maybe just a single leaf moving, right? You don't need to send like all that information again and again. You just want to send the actual changes. So that is inter-frame compression. This is what it looks like. There's three types of frames in inter-frame compression. An iframe is the complete picture where you start from. It can be decoded without anything else. We have a P frame, it's a partial frame. It contains only the diff, only the changes from the previous picture. And a B frame, it's a partial picture that is a modification of previous and future. So it depends on the future. And that's pretty much how video is encoded over RTP. And finally, how do we deal with unpredictable networks? We deal with it using RTCP. As I mentioned earlier, RTCP contains statistics such as jitter and the actual number of packets which were sent, the packets which were dropped, things like that. And RTCP allows for a PLI to be sent, which is a picture loss indicator, whenever the decoder is unable to decode a full frame. What this will do is it will encode one full frame, which has no other dependencies, and it will send it. And sometimes you don't really need the full frame, you just need a single packet. You can just send a NAC. A NAC is a not acknowledged. And you might be wondering why we need all this is because usually ICE connections take place over UDP and not TCP, so there is no built-in mechanism for error correction. We have to do all this using the application layer protocols. Finally, RTCP also includes sender and receiver reports. These can be fed to other complex bandwidth estimation algorithms like GCC, Google Congestion Control. I'm not going to get into that. Just an exercise for the viewer if you're interested in this space. Yeah, I'm open for questions. Yes, please.
Okay, I just wanted to get your thoughts on the successor to WebRTC that's currently working its way through the IETF process, the Amogh effort. Are you familiar with that?
ORTC?
No, MOQ, Media Over Quick.
No, I actually am not familiar with that, no.
Okay, so, okay, anyway, in that case, I strongly suggest you have a look at it and see what's happening over there. It's an effort that I'm personally engaged with, because we're really looking at a lot of use cases that basically look at Amogh becoming the successor to WebRTC for both real-time as well as streaming, non-real-time use cases.
Right. Yeah, thanks for the info.
First of all, thank you so much for this presentation. It was a really detailed presentation, learned a lot.
Thank you.
I have a question. The question is, a few years back, I was trying to build a video streaming server. And what I understand from WebRTC is that it is more optimized for peer-to-peer connections. And so I used HLS for a master-slave architecture. So I wanted to ask, can WebRTC be optimized for master-slave architecture? And would you recommend that?
Yeah, okay. So pretty much every single video chat that you go through is actually a sort of client-server architecture. It's not using peer-to-peer connections. I mean, it is using peer-to-peer in the sense that the peers are the client and the server. And the reason for this is when you get beyond, let's say, 3 or 4 peers in a single call, you're going to run out of bandwidth pretty much. So the way that they do this is they have a single server, which is an SFU, a simple forwarding unit, or an MCU. Basically what they do is you send your video to them and they send you the other client's video back, and you don't really have to deal with a lot of the bandwidth challenges that come with sending video to every single peer out there. So yeah, in production pretty much everyone uses WebRTC in this way.
All right, okay, that's all.
Someone there? If you speak up, I think I can hear you. Mm-hmm.
So in your experience, how common is it for just turning to work out and without the need of calling out to a server?
So in 98% of our clients' use cases, so I work at Dite, we offer audio and video things, audio and video SDKs. So in our experience, 98% of clients are fine using just turn. But for those 2%, turn is really important. So yeah.
Okay. And you mentioned I forgot the terminology that you used for multiplexing videos together. Does turn play a role in there as well? Because turn might have the ability to club video streams so that a single socket can be used.
No. Turn is purely just for forwarding data.
It just relays.
Yeah, so your SFU, in the question I mentioned, the SFU or the MCU, they can do that. So the MCU, what it does is it actually encodes the receiver's videos into one single video.
Yeah.
So it takes up a lot of encoding power on the server side, but it really reduces the bandwidth requirements for all the clients. So if you have used WhatsApp calls, I believe they use an MCU called Currento.
Okay. That's basically just a client participating in the video call, talking to a turn server even probably. If
Sure.
the component that you're speaking.
I'm sorry to interrupt. So we are very tight on time. So if we can take.
Yeah,
Sure.
I'm sorry.
Sure.
Just hit me up after the.
Round of applause for Amogh. What a wonderful session.